lot of times more than one. You'll probably see this on multiple choice and then possibly again on, or some form of this on the free response as well. Whenever you're dealing with these problems, they're very common. So we've got in our, what we'll be looking at here is position, velocity, and acceleration and how those are compared. So position, there are different letters that they will sometimes use for position. Sometimes you're moving along the x-axis, so they'll call it x of t. I've also seen them use s of t a lot. There's not necessarily a standard letter to use for that. They could use any letter for your position. And so for a position graph, that's whenever you have some sort of time here, hours, days, months, years, whatever, and you have a distance here. A lot of times we're going to see it's a distance from a certain point, so it might be your distance from home or something there. Sometimes it is a theoretical question about just like a particle moving along the x-axis. So the origin is where you're comparing your distance from. So if we take the derivative of position, so if we take the derivative x prime of t, or s prime of t, or whatever you're using here, it is going to give you your velocity graph. Because if you think about what we looked at yesterday, x-axis would stay the same, right? And then our y-axis would be change in y over change in x, so that would be distance over time. I like thinking of it with actual like units. So let's say this was, if this was hours and this was miles, now this is still hours, this would be miles per hour. It's easy to, when we hear miles per hour, we think velocity, right? Or at least speed there. So velocity is the derivative of our position. Then we can take the second derivative. So it is the second derivative of our position formula, or the first derivative of our velocity formula. That gives us acceleration. And again, if we're thinking of time being here, such as hours, could be any unit of time, then if I'm doing the same thing here, my change in y over change in x, for my first derivative, I had distance over time, and then my x is time, so distance per time, right? I'm going to use d per t, just because I can't write all that out. Or if we're thinking about our units, it'd be like miles per hour per hour. That second derivative, in a lot of contexts, it really confuses me to think about. I think velocity is one of the easier ones to think about because you guys have all experienced acceleration, right? Every time you get into a car, it is stopped, and you have to accelerate to get up to the speed limit. And since most of you are teenage boys, you probably accelerate faster than you should if you're typical. Yes. Braking. It's true. It's true. Well, if you brake too hard and start sliding, that could cause you.
I almost crashed somewhere at the beach last year. This car like Virginia brakes and was battling my car on the way down there. And he called off the corner, start braking itself or something, almost rear-ended someone at a stoplight.
Connor doesn't even really
I was
have
like,
to drive his
brake,
car. He
brake,
just-
brake, and then we just,
Regenerative brakes?
yeah.
What does that mean?
I mean, there's how many brakes and charges the battery.
Yeah, it's so when you start braking, it brakes harder by itself. It's sort of like hybrids and EVs. So the friction generated by the brakes creates.
Yeah. Yeah.
Crazy.
Yeah. So,
No, you almost,
Okay.
you were good for most of it, except for that one part
Yeah.
where you thought
So-
A good driver
you just thought the car would stop itself for some reason.
how many of you guys can drive stick shift? Okay. That's what I thought. They don't make them anymore, though. Like, you don't even have the chance.
They do.
I can
Just
give
have to
you
find the
I
right
can
car.
give you-
Pretty much in,
I've driven a track.
other than getting something old. They
Volkswagen still makes some.
Yeah.
Sports cars make a lot of.
Yeah, sports cars and some.
What's the oldest car? 28. You gotta.
My first two cars were stick shift.
Adjust the timing and.
Now what?
Yeah, my
Yeah.
grandpa's distributor and the engine.
Huh?
Yeah, I had to adjust the
Yeah.
distributor. in
My grandpa's got
83.
an old 20 model something too. I've never driven that one. But
Drove it. No power steering, no power braking, four-wheel drum brake.
I drove a Tahoe one time that the power steering had gone out on, and that was terrible. I had to do, yeah, mine had, I had, and then when like I got parked, I had to do like a 20-point turn to get out of where I was at because it was awful. You need that power steering, particularly on new vehicles that are designed for it, because older vehicles at least were designed.
Zach Darnell's full of plane. He's kind of got his feet.
That's a good point.
Yeah, yeah. So acceleration we have experienced, but this applies to lots of situations. So like when we're talking about the rate of change of the rate, like we're on some of the other problems, it's kind of hard to think about what's happening. If you think about the snow problem, what would it mean? It's, for me, it's so hard to think about it whenever they're not both positive. But what would it mean if you had a positive rate of change and a positive acceleration in the snow? It's snowing harder and harder, right? Like you got more and more snow coming down. So this is the rate of change of the rate of change. So we could say that the amount of snow is increasing at an increasing rate for a snow situation.
Exponentially and exponential.
It doesn't have to be exponential. If it were exponentially exponential, it would definitely be increasing at an increasing rate. But it doesn't have to be exponential for this to be the case. But you will see, it doesn't have to be exponential, but it does have sort of like some of the same characteristics of an exponential. You got to be, starting off slow and then your rate increasing. It's got to be concave up, right? What becomes confusing to me is to think of having positive. So what about if you have positive velocity but negative acceleration?
You're increasing at a decreasing rate.
You're increasing at a decreasing rate. So you're increasing your distance. So you're still moving forward, but you're slowing down. What's that like for the snow?
It's starts to rain.
No?
It's snowing less.
It's still snowing, so your snow is still
You're
accumulating,
getting towards the edge.
but it's slowing down, right?
No.
If it turns to rain, it's going to start melting the snow on the ground, and that is going to mess up your model is no longer going to apply.
The ground is colder than the air. Yes.
I think if it turns to rain, it's going to mess up your equation. But so, to me, sometimes it's a little hard to think about what's happening for these. But I think acceleration is one of the easier ones to think about because you have experienced that. So, we got an object that's moving along a straight horizontal line so that at any time t from 0 to 9, its position is given by this equation. So this is really common for you to see these like naked physics sort of problems. Do you guys do any of these in physics where you just got like a particle that's moving? You may not as... Yeah, it's you may not look at it as much because you're using the algebraic equations instead of the calculus to get each one. But I know that whenever I was in physics in college long ago, it seemed like half of the problems we did started with a particle in space is moving along a straight, or two particles collide, or it was always particles. So in physics, you look at a lot of just a theoretical particle rather than like a car actually moving. So we'll see some of both. But so x is giving us position. We'll know the velocity of the particle at t equals 5. Is it moving to the left or to the right? Okay. So if I want to find velocity, what have I got to do? Take the derivative. This is a pretty simple derivative. Here is my suggestion to you. You need to call this x prime of t, because that shows you are taking the derivative of x. However, this is velocity, so I always say equals v of t. We're renaming that as v of t because v makes us think velocity. You don't have to do that step. You can refer to it as x prime of t for the whole problem if you prefer. But you don't want to just call it velocity without showing that you took the derivative. So I would do it this way every time. And then our derivative here is just going to be negative 3 plus 2t. And particularly, we are interested in the instantaneous velocity at t equals 5. So what have we got to do? Plug in 5. Once you have written v of t equals x prime of t, you can call it v now if you want, or you can call it x prime. Either is fine. So we would have negative 3 plus 2 times 5, which is going to give us negative 3 plus 10, so we'll get 7. All right. So our velocity is 7. This problem doesn't have any units in it, so we can ignore units for the problem. We're going to see some others that do have units where we got to think about them. So the other question is this particle moving to the left or to the right? It's going to be moving to the right, because if it is moving along the horizontal line, you are going to consider like it's the x-axis and the positive direction is going to be to the right. You have a positive derivative. So we would say since v of 5 is greater than 0, the particle is moving to the right. Velocity does include direction. So when you have positive, that is going to be the positive direction that you're looking at. If it's just a straight line, it's generally going to be right. And negative would be the other direction, left. Sometimes it may be up or down. Sometimes it may north or south. Sometimes it may be towards home or away from home. Sort of. Or, yeah. So. We will not, because that would be sort of like some vector problems, and we do not do those because as far as calculus goes, it's a Calc 2 concept. Like, you have to have, I think, well, they can be done. So pre-cal is sort of like when you're doing vectors, it's like a algebra-based version of it. So when we look at them in pre-cal, it's an algebra-based version. For you to do calculus with them, it's not something we're going to deal with here. Or at least I have not seen problems with it. There might be something you could do with it, but yeah. I think that you will I'm pretty sure it's Calc 2 where you see it, or if you take Calc-based physics, you'll do a lot with it. But we do not get into vectors that are, we only do vectors like opposite direction vectors, because this is kind of like an opposite direction vector sort of issue right here. We do not deal with ones that are like 90 degrees to each other, or certainly not ones that are like 30 degrees to each other here. So that would be more of like a Calc 2 concept, I think, if I'm remembering things in the right class. B says, what is the acceleration of the particle at t equals 5? Is the particle speeding up or slowing down? Okay, so acceleration, what have I got to do? Second derivative. So you can call it x double prime if you want, but you don't have to, because you've already said, assuming that this is a problem where you've got like a part A, part B, they'll assume you already knew what was in part A. So since we've called this V, we can call it V prime of x, or we could call it x double prime. You can call it either one. And that is going to be, I like to call it A of, actually it should be a T. I like to call it A of T because it just helps me so much to see that A right there that makes me think acceleration. But if it doesn't, you can just stick with V prime or x double prime if you want. And what is A of T going to be? 2. And so what is A of 5? Also 2. It's going to be 2 for, you have a constant acceleration here. So, in this case, I need to know if the particle is speeding up or slowing down. Okay? All right, why? Okay, if acceleration is positive, is the particle always speeding up? It's not. So, speed, the key right here is that they're asking you for speed. Not velocity, but speed. If they ask you, is the velocity increasing or decreasing, then you just got to look at the sign of acceleration. If acceleration is positive, velocity would be increasing. If acceleration is negative, velocity would be decreasing. Speed is different because speed does not have a direction. Okay? So, this is something that we need to watch out for, because I tried to go over this multiple times because students forget it and want to just say because acceleration is positive, then speed has to be increasing. You have to consider velocity and acceleration. Okay, so you would have to say, since A of 5 is greater than 0 and V of 5 is greater than 0, the particle is speeding up. You're slowing down. So let's make a chart for this. So this is the answer for this problem, but let's make a chart that would consider all the possibilities, right? So let's think about V of t and A of t, and then we're going to think about what speed is doing. All right, so our first consideration is that velocity is positive, acceleration is positive. For me, this one is the easy one to think about. So think about being in a car and going forwards and backwards, like on a straight road, right? So if your velocity is positive, that means you are going forwards. If acceleration is positive, you are going forwards and you're going faster. You're speeding up, okay? So this would be speeding up. I'm going to put an up sign for up. Okay. This one is also, to me, easy to think about. Positive, negative. All right? So your velocity is positive. That means you are going forward. So you are moving forward. But if you are moving forward, you are your acceleration is negative, so you are slowing down, right? You're going faster, and then you're slowing down. So you're stopping, or slowing down at least, right? So your speed is decreasing here. Now, those match with just what we usually think acceleration is positive, speeding up, acceleration negative, slowing down. But consider this. Negative, positive.
Going in the negative direction, but you're speeding up.
Okay? You're going in the negative direction, but your acceleration is positive. So what does this acceleration being positive, what's that tell us about velocity? It's increasing. So if your velocity is negative and it is increasing, right? If we're thinking about a graph where that's happening, we got time and velocity, so 0, 1, 2, 3. Your velocity is negative, so say it's negative 10, but it's increasing, so what's happening to it? Negative 9, negative 8, negative 6. That's linear, but, whenever you're in a car and you're worried about speed, you don't care about that sign with your velocity, right? So if you are going backwards down the road, if you put your car in reverse and go down 77 at 85 miles an hour, right? You can't be like, police officer, I was not going 85, I was going negative 85 because I was going backwards, so my velocity is negative, right? I mean, if you can get your car to go 85 in reverse, I don't even know if that's possible, but if you can, the police officer does not care about velocity, they care about speed, right? So, if you take away all those negatives, if we think about speed, your speed is 10, 9, 8, 7. Alright? So, if you have negative velocity, but positive acceleration, it's like you're going backwards, but your speed is actually slowing down. So, this is going to be that you're slowing down. Your speed is decreasing. But, if you're going backwards, you have a negative velocity, and you also have a negative acceleration. Now let's think about what would happen with that. Yeah, so you got your velocity might be negative 10 here. If your velocity is decreasing, that means you got negative 11, negative 12, negative 13. Oops. Negative 113, whatever, you're still decreasing. And so speed is actually increasing, right? So that you would be speeding up. So, when you see the word speed, you must consider velocity and acceleration. If they have the same sign, you will be speeding up. And if they have different signs, you'll be slowing down. Sometimes this is hard for me to think about. The forwards, backwards, positive, negative. So if you just remember, velocity and acceleration have the same sign, you're speeding up. If they have different signs, you're slowing down. And that's all you have to use to justify your answer on these things. Okay, questions? All right, let's look at this one, and I think this one will, I think I meant for it to be calculator active. So let's grab our calculators here. All right. All right. All right, so if we do e to the more complicated equation here. We could do that one by hand, I think, but we're going to use a calculator because I'm mostly concerned with the concept. All right, so we've got a position of a particle moving along a straight line at time x for 0 to 20. The first thing we want to do is find the time for 0 to 20 at which the particle is at rest. What are we going to be looking for there?
0.
Of what?
F.
Okay, F gives me position.
No.
Okay.
F prime.
Okay, so if I do when F is 0, that tells me when I'm at the origin or whatever home base is, right? Which, for this case, you're going to usually think about the x-axis. So, at the origin. Are you guys judging my door? You can shut it if you need to look at it. They don't even know about the unit circle. They're not going to realize how beautiful it is. Fourth period actually did most of it for me, but I did the unit circle part because I did not trust them to fill in the unit circle correctly. Hello? Oh, is that your class? Are they? Okay. I thought they were ROTC, so they do know what it is. Okay. All right, bye. Oh, yeah. See ya. Actually, that was Coach Wood's class. They're learning about the unit circle right now, so he sent them down here.
Go look at that snowman.
Yeah.
I'm waiting for him to go on the roof. Yeah. I don't want to go on the roof.
You cannot go on the roof.
I want to hit golf balls off the roof.
If you go off the roof, if you go out on the roof, I will.
What if we go off the roof?
It's probably only like an 8-10 foot drop, but
I want to hit my driver on the roof.
but
What's the only
if any of you guys go off
I want to hit driver off the roof.
out on the roof, I will
Yeah.
first try to get you back in off of the roof because of the peril of the situation, and then I will immediately take you to Miss Burton's office.
See if I can hit one to the roof of the elementary school.
Or if I can't get you off the roof, and I guess if I
hit one to
can't.
that roof, you hit it back.
Yeah. Okay. All right. Let's finish this up. All right. So if we look for where the position is 0, it tells us when we're at the origin. At rest means we're not moving, and when you're not moving, it doesn't matter where you're at. You could be anywhere and not moving, right? So not moving is your velocity, and that is when your velocity is 0. So we really care about when f prime of x equals 0. So there's a few ways that you can do this. I am going to do y1 of x, comma x. I think I'm going to get the actual equation here. It's not too bad, actually. So this is your equation. And we want to know where f prime of x equals 0. And on a calculator active problem, that's all you have to write down. You don't even have to write down what the derivative is. Braden, have you already tried solving? Does it work? Okay. So if we just go to F2, solve, and we're going to go up here and hit enter for that, equals 0, comma, x. It does warn you that more solutions may exist, but if you're unsure, you could go check the graph. But it looks like we got x equals 10.6386 and x equals 0.020858. So the particle is at rest at these times. We're points, whatever you say there. Okay. Questions on that? Particle at rest, velocity needs to equal 0. All right. B says, what is the position of the particle at x equals 0? Plug it in 0 to what? Original function. So we're going to do f of 0. Okay, again, calculator active, you don't have to write anything down except for f of 0. You can do, because you've already got this in y equals, you can go here and just do y1 of 0. And we might, oh, we get 6, so we don't really need to hit the green button. We get 6. So the particle at 0 is 6. Or the position is 6. All right. What is the position of the particle at x equals 20? What do we need to do for that? Y1 of 20. Ooh, let's hit the green button on that one. 12.5435. So f of 20 equals 5. I'm sorry. 12.5. 435. Okay. All right. What is the total distance that the particle traveled?
The difference between the two things.
No. I was trying to get you to say that, but it's not.
The position,
Uh-uh.
f of x, f of 0,
Well, maybe.
and f of 20.
So what Bo has given me, where he said we're just going to subtract those and we're going to get 6.5435, right? That is something that we sometimes care about. That's what we call displacement. Okay, so displacement would be 12.5435 minus 6, which would give you 6.5435. But displacement does not equal total distance. In all cases, it can equal total distance. Someone put most of the time. So it is possible that your displacement does equal your total distance. So to give you an example, let's say that Paul decides he's going to use the bathroom pass, and he goes out in the hall, and he walks down to this bathroom, and it has been vandalized and is shut down. And so Paul then has to walk back to this bathroom to go to the bathroom. So his displacement from this room is a shorter distance than the total distance that he traveled, right? So his displacement from this room is just distance from this room to that bathroom. But his total distance is further because he went the wrong way first, not knowing it was the wrong way. Then he went back down to this bathroom, right? So the reason they're not the same here is because our particle is not going in the same direction the whole time. So if Paul just walks, if he leaves this room and just walks to that bathroom, right? His displacement is the same as his distance traveled, because if we kind of treat it like it's on a straight line here. But if he goes a different direction first and then goes this way, then it is not the same. So we need critical points, which we really already found. What were they? There were these places where our derivative equals 0, right? So I'm going to look at let's look at the graph really of the derivative. Is that what we want to see? Is the graph of the derivative? Yeah, let's look at the graph of the derivative. So in y2, I'm going to put, it doesn't work. Let me go back. I'm going to go up here, take this derivative, copy it, and paste it here. So y2 is my derivative. I think there's a way for me to make that not graph, but I don't know how. Oh, I know how it is. Okay. If you want to keep something there, but you don't want it to graph, so like I don't want to get rid of this because I might still need y1, but I don't want it to graph because I just want to look at the derivative. See how F4 has that check mark right there, and there's a check mark over here? If you click F4, it will make the check mark go away, so it will only graph the derivative for this. So if I go to the graph, well, let me go to window first. We just want 0 to 20, and then if I graph, why don't I see anything at 0.02? I'm going to do zoom fit to see if it'll give me something better here. I think what's happening here, I think this is going to go, I'm going to make my window actually go to -1 right there just so I can see a little better. I think this goes back up and actually crosses right here and we're just not seeing it very well. Usually on like FRQ problems or something, they give you ones you can see a little bit better. Because when we solved it, it told us at 0.020858 we actually crossed right here. So, but I've got mostly a negative derivative, which tells us what? Moving to the right. But then right here, what happens? I'm sorry, moving to the left. And then I've got a positive derivative, which tells me I'm moving to the right. So what my particle did, it actually, this one's a little bit weird because it's, so I think I probably had a positive derivative for just a little bit of time from, if we're thinking about like a timeline here, from 0 to the 0.02, I was moving to the right. Then, until I got over here to 10 point whatever we had, 638, I was moving to the left, and then for the rest of the time, I was moving to the right. So we've got to consider like each interval that happens here. So if I do, we already found f of 0. It was 6. If I find f of 0.020858. All right, so that was my first critical point. And I should be able to do just y1 of 0.020858. That gives me 6.07194. So from 0 to 0.02, how far did I travel? 0.07194. I was going to the right, just like a little tiny bit, right? Then I want to figure out where I ended up at 10.6386. Okay, so I do y1 of 10.6386. That is going to give me negative 11.4609. So I only care about distance. I don't care about whether it was positive or negative. So how do I figure out how far that was? I could subtract the 2, or you could think of it like you're over here at positive 6, and then you go to negative 11 points. So you could add 6 in. Either way, it's going to end up the same. So you got the 6.70194 minus that negative 11, or the double negative becomes like a positive. So you went 17.5328 to the left. And then our end point is 20. We already found it, didn't we? 12.5435. And so that distance, if we take 12.5435 and subtract that negative 11.4096, we're going to get 24.0044. And so if I add those together, then I'll get 41.6091 units. So the total distance is actually a lot more than the displacement, because the particle went in one direction, then it turned around and came back. So it's not very far from where it started, but its total distance traveled is further. Yes?
So from the 0.020858 to the 10.6, you subtracted 6 minus negative 11, right?
Mm-hmm.
But for the next 2 points, you subtracted 12 minus negative 11?
You generally want them, it's an absolute value, because you want it to be positive. So you could, like, if you use absolute value bars, you could just always, you could do, let's see, where are catalog, absolute value. You could do 6.07194 minus negative 11.4609, or you could do it the other way around. It's not going to matter whenever it's absolute value. And then for the second one, if I just subtract the first one minus the second one, it's going to give me a negative number. But you could do, if you do absolute value, so if you do absolute value of your negative 11.4609 minus 12.5435, then you would get that, would be positive as well. Right, right. So it doesn't really matter which one you put first when you subtract. I did it so that I would just end up with the positive already, because I was thinking ahead that this needs to be positive. Because when you're talking about distance, it's always positive. It's not going to be, expect total distance is always going to be positive. Everything about it is positive. There's actually going to be a different way we can learn about how to do this once we learn how to integrate, but we're not there yet. Oh, what you got to say?
You're bringing up for the class.
I appreciate it. Hide that one.
You're going to split it 12
Yeah, everybody get a sliver. Okay. All right, does that make sense? All right. Okay. Particle is traveling on x-axis, has a position x at time t. The graph of the particle's velocity v is shown. Which of the following expressions gives the total distance traveled by the particle over the time from 0 to 5? I think I copied this from multiple choice. Let's see. The graph of the particle's velocity. Instead of which of the following, write the expression that gives the total distance traveled by the particle over time. So our expression is going to be in terms of x of t. It will not be a value here. So what do we see happening right here with our velocity at 2? it hits 0, and it is switching from positive to negative. So if our v of t at 2 is going from positive to negative, that means that our x of t is going from increasing, which would be going to the right, and then decreasing, which would be left in this case, right? We're switching from right to left. Okay, so let's think about what's occurring here. If we make ourselves like a timeline, sort of, we got 0, 2, and we're going to 5. So this is our time right here. From 0 to 2, which direction are we going? We're going right. So I need to have, it would be good, if I use absolute value bars, it would be easier to write this, but I'm going to tell you that whenever you see this with answer choices, it doesn't have absolute value bars. So, and then right here, I'm going to the left. So one way that you could write this, so some options, is you could say absolute value of x of 0 minus x of 2 plus absolute value of x of 2 minus x of 5. Or you could even switch the order of either one of those inside. So if you're using absolute value bars, you got a lot of flexibility. Because absolute value bars wash away the negatives and make it work, right? So this is an option. But I'm going to tell you that when you see this problem multiple choice, it's not going to have absolute value bars. So if we don't have absolute value bars, that means we need to arrange this so that we'll get positive numbers. So if we were moving to the right, x of 0 and x of 2, which one's bigger? 2, right? Because we're moving to the right, which would give us further positive over here. So for this section, that's going to be x of 2 minus x of 0. However, from 2 to 5, we move to the left. So which one's bigger? X of 2 or x of 5? X of 2. So we would want to do x of 2 minus x of 5. There. I think that the question leaves it like that. They don't like combine your x of 2's or anything. You could, because there's 2 of them, but I think they leave it like this. But without absolute value bars, it has to go in this order so that you don't get negative numbers. Okay. You would also have a relative maximum. So you're furthest to the right. If they were asking that question, when are you furthest to the right, it would be at t equals 2. All right. Speaking of furthest to the right, let's look at this equation. They're giving us velocity. We're going to type it in, negative 2x plus 20 square root of x plus 3. Oh, it's not even doing anything. Ugh. Sorry. All right, let's try this again. Negative 2x plus 20 square root of x plus 3 plus 8. Parentheses. Okay, so if I graph that, see if all right, due to our lack of time, let's switch over to Desmos where I can zoom out easier because we're about out of time. Desmos.